Archimedean property and density theorem. First, let us come to the completeness property of R. R is the set of real numbers and it is a complete set. By completeness, what we mean? So, every non-empty set of real numbers that is bounded above has a supremum in R. The set itself, though it is bounded above, may not have its own supremum, but its supremum will always be a real number. This is the meaning of completeness property of R. For example, let us see this particular set, open interval AB. We know that this set contains all x which are greater than A but smaller than B. So what we observe here, A is the infimum. Infimum is amongst its lower bounds, A is the greatest one. And amongst the upper bounds, B is the least. So least upper bound means supremum. So this set has both infimum also and supremum also. But A is not a member of this set. Same way B is also not a member of this set. But A and B are real numbers. This we mean to say. This is the meaning of completeness action. So this is the completeness property. Now let us move to the Archimedean property. Archimedean property says that if x greater than 0 and y are any real numbers, means x is positive, that is the only condition over here, and y is any real number, then there exists at least one natural number n such that n times x is greater than y. So for any x and y, only x has to be positive. So x times n will always be greater than y. So for y you can find out n such that nx will be always greater than y. This is the meaning of Archimedean property. Let us try to prove it. Y is any real number. So y may be positive, negative or 0. If y is negative means less than 0 or equal to 0, then n equal to 1 is enough for us. What will happen if I take n is equal to 1? So y is always less than 0 and 0 is less than x because your x is positive. So 1 into x is sufficient to you. So 1 into x means n equal to 1 is sufficient to us. This is the meaning of this. Now, if we take y greater than 0, if y is also positive, then it is our job to show that surely there is at least one n such that n times x will be greater than y. But because x is not known, y is not known, surely we cannot give the value of n. And we want to prove this in general for any x and any y. So let us go by the method of contradiction. Let us suppose that there is no natural number n such that n times x will be greater than y. What this means? For all natural numbers n, this nx is smaller than y. So let us consider a set S containing n into x for every n, natural n. So this set contains infinitely many elements. What we mean by this set? It contains 1x, 2x, 3x, 4x and so on. Now all n times x are less than y, means y is the upper bound of this set. So set S is bounded above. And completeness axiom tells us that a set which is bounded above and is a subset of R, then by completeness axiom this set has the supremum. So this set will also have a supremum. Let us name it as U. Then for all natural numbers n, this nx will be less than or equal to U. Now U is the supremum. So no number smaller than U can be an upper bound. So U is the least of all the upper bounds. This is what we know. So what we'll do is, we know x given to us is positive. So naturally U minus x will be certainly less than U. So u minus x cannot be upper bound. Means u minus x will be smaller than nx for some n. Now let us add x to both the sides. So what do we get? U less than nx plus x, which is equal to x common, in bracket we are left with n plus 1. But we know n plus 1 is a natural number, and we are getting u smaller than natural number times x. This is a contradiction because we have supposed there is no natural number satisfying this condition. So that fails. Means our assumption is wrong. Means there must be at least one n for which n times x will be greater than y. So hence the archimedean property, that is true. Now let us see corollary to the Euler's archimedean property. First one is, for every positive real number x, there exists a natural number n such that 0 less than 1 by n less than x. Means what? You are given any real number, positive real number x, you will certainly find a natural number whose reciprocal is still smaller than that x. So if you tell me that my x is suppose 0.9 something, this is the value of x. So very naturally I have natural number n. If I take it to be 100, 1 by 100 is 0.01, and which is certainly smaller than 0.9. So this is just verification of this statement. This is not the proof. But we verified, yes, for a positive natural number, for a positive real number, we will certainly find out some bigger natural number whose reciprocal will be smaller than x. And why to write 0 less? What does 0 less mean? 0 less means this is positive, and a reciprocal of a natural number has to be positive. Okay. Now let us go to the second corollary. For any positive real number x, there will exist a natural number m such that m minus 1 is less than or equal to x, strictly less than m. So this is also very sure. See, if we take any real number, a real line, suppose this is the line that we consider. So we know very well on this real line we can have points. We can have points. So you can see this is our 0. You can go for 1. You can go for 2. And so on to this side. I'll go for 3. Here it will be minus 1. Here it is minus 2. And so on. You'll have minus 3. What we are saying, for any positive real number x, positive means will be to the right side of the 0. Very naturally, every real number you can plot on this line. So before that real number and after that real number, you will have natural numbers. So your x will always lie between m minus 1 to m. Now if you are handling 2, means you are handling a natural number itself, then it will be equal to x. That's the thing. So it is so simple. Now let us deal with the density theorem. The statement is very clear. Between any two real numbers, there is a rational number. Between any two real numbers, there is a rational number. So for the sake of simplicity, let us take two real numbers and let us clarify which is smaller and which is bigger. So we are saying x is less than y. X and y are any two real numbers that we are handling. So from the bigger number, if I subtract the smaller one, the resultant is a positive. So y minus x is greater than 0, so I got a positive real number. Now by the Archimedean property, there exists a natural number n such that n times this positive real number will exceed 1. It is, of course, 1 is a fixed real number, we know. So n times y minus x will be certainly greater than 1. Now let us open this and just simplify. What do we get? Ny is greater than 1 plus nx. And obviously 1 plus nx will be greater than nx. So we got this inequality. Now let us apply the corollary to the Archimedean property, that a real number lies between the consecutive natural numbers. So nx lies between m minus 1 and m. This is the corollary to Archimedean property. Now let us add 1 throughout. So what it gives? M less or equal 1 plus nx, which is still less than m plus 1. So we have got two inequalities with us. Let us highlight them. So this is the inequality and this one. Okay. Now if we combine the results, what do we get? So let us start. Nx is smaller than m. Yes, observe here. Nx is smaller than m. Obviously, m will be smaller than 1 plus nx from here. And 1 plus nx is still smaller than ny. So we combined those results and we got this. Now I just want three things from here. Nx, m and ny. So let me have it. Nx less than m less than ny. And let us divide throughout by n. N is a positive natural number. We know it's positive. So the inequality remains the same. So what we are getting, x less than m by n less than y. And we know better, m upon n, natural number upon a natural number, is a rational number. So between any two real numbers, we get a rational number. That's all. So that is the proof of density theorem. Now let us have corollary to density theorem. So between any two real numbers, there is an irrational number. When we are asserting for rational, what happens for irrational? So the same thing is true for irrational number also. So that's all. That is the theory regarding real numbers which we must know. Thank you and bye.